Today's daily, 2684, maximum number of moves in a grid. You are given a zero-indexed n by n matrix grid consisting of positive integers. You can start at any cell in the first column of the matrix and traverse the grid in the following way. From a cell row call, you can move to any of the cells, row minus call 1. Okay, so you can move... Okay, so you can move to the right and you can go up, down, you can go on the same line, up or down, such that the value of the cell you move to should be strictly bigger than the value of the current cell. Return the maximum number of moves that you can perform. Ooh, okay. Maximum number of moves that you can perform. That's good. Okay, so you had to find... Okay, that's a good one. How do we do this? So, Kyle's initial thoughts. What you could do, you could brute force it. And what you would do is just basically try every move. Actually, now that I think about it, this feels like if you turn it on its side, this feels like a depth first search. Maybe it's actually not brute forcing it. Maybe that's actually a reasonable thing. Though, is there anything we can deduce? Is this like dynamic programming? Should we build up our solution? That's also a possibility. We could do like dynamic programming. So the depth first search would be just go with the highest row possible and backtrack. That would find a solution. So basically you start at 2, you go to 4, 3 doesn't work. Okay, so you try 9. Okay, 9 works. So now you try 5, that doesn't work. You try 3, that doesn't work. You try 11, that works. And then you get 4 because you've reached the end. That would work, but I think we can do even better. My dynamic programming idea is that you only need to know if the prior state is true, if you can get to this one, and if that's greater than that one. Let's see. So all the nums are going to be greater than 0, I'm assuming. Yep. So all the numbers are going to be greater than 0. So you could have like a fake row of zeros, and that's your starting place. And then you could just, let's see. So we have then 2, 5, 3, 10. Oh, you're messing up my grid. Then we have 3. Yeah. And so basically what I mean is you could just check to see if you could reach a cell given the prior rows. So all of these ones are true. 2, 5, 3, 10, they're all true. In fact, we don't even really need this 0 thing. That was just the idea to get the recursion started. Or not recursion, but iteration. And then for each cell in the column beyond it, you would say, okay, is there something behind me that can be reached and is there something behind me that can be reached and is less than me? So come to think of it, I actually think the depth first search is the better way to go, because this will check all the possibilities. But depth first search, well, it could take a while. If the solution is all the way down here, we're in trouble. I guess the depth first search, it only really finds something if you immediately... Yeah, I wonder what the topics are. I'm betting that they're depth first search and dynamic programming. Oh, okay, well, it's just dynamic programming, but I still think that that would work, just probably not as well for bigger solutions. But yeah, so for every column, check for every column, for every cell, check that there is a cell in the column prior that can be reached and is less. Okay? So for that, we could have a DP array, and that would just be really like, would it be column row? Because we're really working with the columns here more than the rows. You know, we're going through each column one at a time rather than each row. Contains bool value for if cell can be reached. So we would say okay, so m by n. Okay, we'll just say m is the height and n is the width. So n equals length of grid, and n equals the length of grid 0. What are the conditions here? Are we guaranteed? Okay, well, okay, the grid's going to be at least 2 by 2 based on these conditions. Cool. So now we'll say dp equals false times n. I always mess this up. False times n for in m. Okay, so this will set up a grid of falses that's equivalent to this grid right here. Now we know that you can reach all of the first rows. So actually, I think I flipped this. Would it be just easier to understand if I kept it the same dimensions? Because I'm thinking about flipping it. I'm thinking about making it like that. So it's actually on its side, which would be easier because then we could just access. This might make things too complicated, but it might make things easier along the line. Because then you could just say for I in m, or you could say dp0 equals true for I in m, or true times m. Because you can reach, so set up matching bool grid for whether you can reach a cell. You can reach all the values in the first column. Okay. I'm going to make a note. Grid is flipped. I kind of like it being flipped because then we can do this instead of having to iterate. Because we're working with the columns, we can then just handle all the columns at once. Well, a column, all the rows within a column at once, instead of iterating through all the rows and getting the same column. Really not that costly, but this just kind of makes sense in my head. Next part. So now we say for every column, for every cell, check that there's a cell in the column prior that can be reached. So for C in range, so we already did the first one, so we don't need to do any, for C in range 1 to n, okay, so that'll iterate through all the remaining columns. And now we're going to say for R in range M. Okay, so C and R are the same thing. We have to flip it when we're accessing the DP array, but we don't need anything else. So now we're going to say check that there's a cell. And then what's nice is if no cell is true now, you stop. Meaning that if you can't reach any of those cells, you stop. So that's how we stop the recursion. Okay, so for every column, for all the remaining columns, for all the rows, what we're going to do is say let's see. We need to make sure we're not going out of bounds here, which is frustrating to say the least. Why don't we make a helper function? Define has predecessor. Okay, and this is given an R and a C value. And this will return just a Boolean. Has valid, yeah, predecessor has valid predecessor. Okay, so more specifically, this is going to check the 2 to 3 values behind to see if they can be reached, and to see if they can be reached, and that they are less, and that one of them is less. Okay, so we know that we can do the same level, so we can say if grid R C minus 1 is less than, we'll say, I always say current cell. equals grid RC. If grid RC minus 1 is less than current cell, and we also have to check that it is the same way in the DP array, so it would actually be C minus 1 R. I think that should line up. So if you can reach the prior cell and the prior cell is greater than this one, return true. Now we do the other conditions, but we have to make sure that they exist. So this would be C minus 1, R minus 1, but we have to make sure that R is greater than 0 before we do that. But that should work. And then we do the same thing, but R is greater than M. R is less than M minus 1. Got it? All right, so this is saying take the current cell is the one directly to the left less, and can that cell be reached? Honestly, at this point, you could just say return this, because if it's reached this, then if this isn't true, then it's false. So you might as well just say return this. Try the row above, and first check there is a row above. Finally, try the row below if there is one. Okay, cool. So for C in range, we could just say DPC equals, this is going to be cool, has predecessor RC for R in range M. Cool. And now we're going to say if not any DP can you start, do you have to start from the left side? Or can you start from any move inside? No, you have to start from the left side, otherwise you can do 1 to 4. If not any DPC, return max path. This actually might work. That'd be cool. And then just return max path. This is if you make it so. For all the columns, set the DP column values to the bool value of if that cell can be reached. So what's the time here? I actually think this might be ON time. Let's see. Because we have N cells in the grid. This, sure, it checks 3 cells per cell, But, you know, that would just be 3n. Right? Yeah. For every cell, you check 3 cells. It's not checking up to the max of the grid. For all the columns, you say so, and then you iterate through the columns, but you're only iterating through one slice of the columns at a time. So this might actually be pretty fast. Runtime error. I always mess this up. I always do. Oh, because I didn't do the bracket. Is it this? And now that one's mad? Oh. Because I didn't put it in brackets. I didn't put it in parentheses. Oh. Because I didn't do the write any function. Wow. Syntax is off today. Wrong answer. Oh, is it just... You can make 3 moves from the starting cell, so it just one off. Kapow. Come on, give me that. Woo! Let's go. Oh, that's awesome. Really happy with that. Really happy with that solution. And on my checklist today, we had dynamic programming. So I got that out of the way. That was a great problem. The depth first search was a great... I don't even know if that's a red herring necessarily. But I think the backtracking could be kind of costly. I really like the flipped grid so that we can just access a whole column at once. That was nice. And yeah, we're just saying, okay, so we have a grid, and that grid, to reiterate, we have a grid, and that grid corresponds to the grid of cells, and it's just saying if that cell can be reached. If that cell can be reached, set its value to true. So, for example, all the first values, you can reach them. You can reach these this first column for free. So that's true. Then we say, take the current cell. Well, we have a little helper function that checks if there is a cell before it that can be reached, and if it's less than, and if it's less than. Then we just do that for all the cells in every column, and we stop once a column doesn't have a cell that can be reached. Woo! Let's go, and not that costly on time on space either. Yeah, this looks like the same thing. Found indicates if we can reach any cell in the current column. I like mine. Okay, I'll upvote it for Jesse. I'll upvote it for Jesse. Where is it? Where's the upvotes? Oh, here it is. Yeah, great daily problem. Awesome problem. Dynamic programming. It seems hard at first, and then you just do more of it.